I guess it's the home stretch of the workshop, and I also would like to actually add my personal thanks to the organizers both of the program and of this conference. It's been absolutely fantastic. I learned an awful lot, and I should say that, you know, in preparing this, I also thought, when was the last time I actually was here at one of these programs? And the way one does this now, I go to my iPhone and see when the last time was that I actually took a picture in Santa Barbara, right? That's the safest way to do this. And at the time, I actually ran across the following picture, a student that was admitted to the workshop in 2019. And did you actually have a desk, or did you don't get to as a grad student. Oh yeah, anyway. Thank you for letting me into this workshop. Anyway, let's go back to Gaia DR4, because this is something that has been mentioned often, but so far always kind of side sentence. Winter's coming, or technically spring, because it should be a rather beautiful spring that is coming. And what I'd like to do is actually talk about this, because I do believe it'll be tremendous, and I do believe it's actually important repeatedly to wrap your mind around what one would do if you care about this topic once you have Gaia DR4. So what I'll do is I spend probably the first half going over what Gaia DR4 will actually give us, but then also delve into a few more things, you know, what will it actually take then to get low-hanging fruit? What work? Will it be easy? Will it be obvious what's in there? And if you actually want to go to the regime that our gravitational wave colleagues have been in, that you have a whole bunch of things, and you have to think harder about how to actually do population models, right? That also brings up the question that what models one should consider. And I will also speculate on what my, at least personal view is, that which part of parameter space for black holes and binaries DR4 will open up. Okay, so, but let me start by showing you this, and I should say there's actually a very nice talk that Anthony Brown has given at the European Astronomical Society annual meeting. It's public, you can find it there, which is a nice summary of what is coming up. And so let me first walk you through the things that perhaps feel incremental, and then let me tell you what I think will be qualitatively new. And before doing this, Anthony Brown is basically the lead of a thing called the DPAC, the Data Processing and Analysis Consortium. And let me just perhaps, you know, because it's often, Gaia data don't just happen. There's a large group, 50 of which actually in the coding trenches, that are spending an enormous amount of effort getting this working with the commitment that their job is to produce the data so that all of us can have fun with it. I'm saying this in part also, if you're having fun with it, consider actually also including some of the pertinent DPAC members in your signs. So, first thing to say, well, it's only twice as much data. And of course, for parallaxes, that only means you're doing a factor of square root 2 better for proper motions, the square root 8, and for accelerations, etc., to the 5 halves. So that's perhaps the obvious thing, even if you just look at the long time baseline, that is actually quite a leap. But as I'll show you, it's the qualitatively different things that will come out that will make the biggest difference. So I think it is now politically semi-settled that it'll happen in December. Current best guess is it'll be Hanukkah friendly, not Christmas friendly. So that's my time window that I perceive, but we'll see. Let me now just walk you through perhaps the banal things. So what's shown here in these plots is the parallax precision as a function of magnitude. Fine, square root 2, don't write home about it. Proper motions, square root of 8, that's already getting more serious, so I think that's good. Another aspect of it is also kind of illustrated here, and the topic came up, Gaia is struggling in crowded fields. Like what's shown here is in the LMC region, how in different processing, if you were to just go take the old code to DR4, systematics would be more significant. So there's also improvement of the data analysis that has actually entered that makes things better. But I've taken this slide directly from Anthony Brown. It's a little hidden what I think is actually the most pertinent thing here, that indeed there will be, I think, close to 10 to the 11.5 individual astrometry points. So the words are chosen here just as a reminder. Correctly, it's epoch astrometry. And I forget, you can read it up in the Gaia mock paper. It's in documentation. And I think one of you guys mentioned it. Gaia does not. That doesn't mean you get alphas and deltas as a function of time. You get 4 funny variables that have to do with scan direction, scan timing, etc., etc. So that just put on. It's straightforward, but not trivial to convert this into position. So this is another case where one might want to do a little bit of software homework to be in shape. Then, of course, for here, the big thing is this blast from the future that is here shown from Gaia Black Hole 3. I think that's, yeah. That indeed there will be individual epoch astrometry, but again, that's the 1D positions with which you can do many beautiful things. And for any object where you do or don't believe the orbit solution, or you think, oh, perhaps there's a triple, you can refit it on your own if you care. It's also true that given the wealth of data, there will be, the Gaia team has the problem, what can you actually publish? Because life is complex, and if you start publishing single orbits, probable binaries, probable triplets, you go crazy. So I think there's a serious set, and I think one should have sympathy that they tend to err on the conservative side, but just here, for the triplet friends here, there will also be, this is the astrometric side, and then you go to actually fitting the radial velocity curve with the triple system. That's my interpretation of this plot. Again, I've taken this from Anthony Brown, and this is their attempt of giving a teaser flavor without giving away the form. I'll skip over this. I just noticed photometry will be better. And the only thing that's remarkable about this plot is that it's actually a base 10 logarithmic y-axis, right? So it may not look like much, but it'll be a lot better. Okay, the second part is that there will be 10 to the 9.5 individual epoch radial velocities, which shown, for example, here on the right side. And I want to spend a little bit of time on talking about the spectra, because A, they're very close to my heart, and B, I think they may be qualitatively the other big, huge new thing, not only individual epoch positions, but also velocities. So this Gaia has a real spectrograph that's in the red. It was once done to do the calcium triplet, which is just in cool stars a nice line to do radial velocities. If you were to care about abundances, there's a lot more stuff in there. But there will be, those will be published not only for each source, but also for each epoch. And just to show off, at the top there is actually a Cepheid and its radial velocity curve. So that is delightful and pretty. The precision will be, of course, a function of magnitude. But for me, what I see is I think the velocities will come in. Black holes are heavy. Induced velocities, at least in short orbits, are large. So I think for all short orbit things, those velocities are plenty good. Now, one part of, we've talked much about massive stars and their black holes. That's, of course, the obvious place to look. All Gaia black holes have been measly little solar mass kind of things. And that has been because, I'll show you in a second, to A, because massive stars are rare far away, which is bad for astrometry, and for complicated reasons, Gaia hasn't done radial velocities for hot stars. So here just a quick flash. While this spectral region was taken for the calcium tripleting cool stars, it actually has the beautiful Paschen series in it. You will have to be a real spectroscopist because that star is just a little cooler. It's the calcium triplet line. It's not a binary. And the resolution for hot stars in many ways I think will be good enough because they often rotate. As you can see at the bottom, that I think is just rotation. So I showed you those. They're actually real. But indeed, all the way down to, I think, 16th magnitude, you can't, 16th magnitude, you will get every spectrum down to signal to noise of 1. So you can be snobby and say, if it's not pretty, I'm not doing it, or you can be strong. I think where it will come in, if you have a particular conjecture, hypothesis to test, you have an astrometric orbit, you want to see whether something's happening in the spectra. There's much to be learned from 39 spectra of signal to noise 1.5. Okay, and the last part, these are these low resolution spectra that spectroscopists refuse to call actual spectra. They're very precious. What I want to mention is also for those, you will actually get, at each epoch a few percent spectrophotometry. So you actually get to see whether anything varies in the spectrum if you care about an object. We've also heard quite a bit of things of objects that are on their way to becoming black holes, those who try to become black holes but failed, etc. So I think it's this time domain part that will be the most precious one. So to kind of summarize this part, there will be billions of individual spectra, and there will be tens of billions of individual astrometry points. There are also light curves, but I think they're, compared to what else is out there, not that impressive. Okay, so now, this is a room that likes to look at the freaks among the Gaia sources. So I have, just for the moment, to be discarded in 20 minutes, the GUIs, the Gaia object of interest. Aside from just, I do think that if you're not careful, the nomenclature of all of this stuff will be a complete mess in 2 years. I feel like one has to go into some sort of limbo before you get elevated to BH in paradise. So that's kind of my sense of the situation. We'll have to see. And the question is, will everything that looks like a black hole actually turn out to be one? So if I try to now put myself into what should one do if one is actually DR4 has happened. So the first thing one should probably do is, okay, there's a whole bunch of crazy sources that look like black holes, look like this and that. I think it's good to actually take a second and not go frantic right away and think about it. I think even then, it'll be important to verify, I guess, one of the first papers we did after DR3 was that, well, some of the most obvious candidates are mass transfer. My feeling is that these time domain spectra, the spectrophotometry, Gaia now has a lot more stuff where you can check, does that object look boring in all the respects that it should? And does it behave interesting in the respects that it should? Then, of course, I think if I just mentally go through what I think will happen, then there will just be objects, and many people in this room, the creative juices will start flowing. How could this object have come about? I think then kind of the next stage is there must be stuff in there that's tremendously interesting that we haven't looked at, that can be the, can I fit the astrometry of the Ogle lenses? Can I dig in deeper into the spectra to find something here? And by the way, I forgot to say on the nature, I think taking the spectra to make sure the thing is dark or one component is dark will be crucial. Then I think it is time, and I'll tell you there are plausible estimates that things of great interest will be in the dozens. It's time to think about how you actually, so you have so and so many objects, what do you learn from it collectively rather than getting excited about each object? And then, of course, there's the long run that, of course, once you have a good model for what the population looks like, bumps at 9, 35, et cetera, solar masses, how you put it in the broad context. So I think that's my conjecture of what the sequence of events is. And I think it'll be interesting to see which parts of the community decide to skip which steps, but anyway, that's... So let me now talk a little bit about population parts and selection function, because that's also been a hobby horse for me, because I think very quickly we'll come to asking how common are the various objects that one finds, right? That's a logical thing to ask. Why did I put this plot on here? It turns out the top version of that plot has been shown about 4 times more often at this workshop than the bottom plot, even though this is distance. That contains also a great deal of interesting information. And of course, if you find one, you can say, hey, it is 5 times closer than, so it must be 100 times more common, right? Once in that regime, you can do some very simple things, but the question is what to do next. And because in the end, ideally, and again, that's following, hopefully in a year and a half, in the footsteps of the gravitational wave community, we want to get the true, we'd like to get the true space density as a function of the black hole mass, stellar mass, period eccentricity. My conjecture is there won't be enough objects to really sample this 4D space very thoroughly. And then one of the nice things about galactic black holes is that, of course, you have the added information, metallicity, age, environment, etc. And right, there are 2 things you must somehow get under control. Know thy selection function and know thy contamination. I think at first there are ways to deal with know thy contamination, because if you go to low mass stars, right, in BH3 there isn't that much contamination, it probably must be one of these. If you go to the massive stars, I think know thy contamination will be a huge problem. But no matter what you do, you need to know your selection function. And let me just, as the one general comment on selection function, a reminder that by the time you end up as a GUI, there have been many things. It must have been an object that made it into the Gaia catalog in the first place, had good astrometry, had an orbit solution, you can perhaps bypass this, must have gotten a spectrum, etc. And each step, right, are Boolean ands, which basically amount to multiplying the selection functions. I also mentioning the first step because one of the big outcomes, at least for me personally, of my 2019 program here is that we actually made a big effort to do the Gaia selection function, which at the time, this is just the simplest. What is the probability that if you're a 21st magnitude object, you're actually in the catalog to begin with? You notice, and it's been said by our Microlensing friends, Gaia's not doing well if you're looking at the galactic center. Sure. And so there's actually, there is some software how, if you want to put together different pieces, you can do this. Okay. Now, let me, on the selection function, do a few more things. Namely, let me just show example from Pranav. One way to do this is to take a good model, such as a cosmic or any of these, propagate it through all of these effects, and see what you would expect. And I think it's a summary. The first thing you see in DR4, you should expect 10 times more than in DR3. A slightly simplified version of this but we only saw 2, not 17, so let's divide by 8, and then 125 by 8 is my best guess at what might come out for. So I think that's, I'll come back to why that's a sensible thing to do now, but taking a model that doesn't fit and scaling it up and down is not the right thing to do if you have 20 or 30 objects. Then you can also, if you want to fit another model, you can just try to show the selection function generically. And now here, because Ben doesn't like to show slides, I'm showing his plot on the slide, right? This is the plot we showed as function of period. In the, when do you get an orbit? When do you get accelerations? Of course, one would have to make a similar thing for Gaia DR4. And here, actually, Kareem on the side while running a workshop has been doing some math. This is just an estimate of what are the chances of getting astrometric binaries if you have massive stars. And of course, this is DR3, and given that the nearest O star is what, almost a kiloparsec away, it's perhaps not surprising that you haven't seen much. This is Kareem's forecast for that regime, right? And also, if you go out to here, and it's a 2D thing, again, it comes back to we should expect 10 times more. Problem is, we haven't found a massive star yet in Gaia, so 10 times 0, we'll have to see what that comes out to be. But even if you have the selection function, this is something where I'd like to get some input. The question is, how do you actually model this? And let me just qualitatively sketch the three things that are rattling around in my mind. Right? You can take cosmic or popsicle any of these models, project them into the space of observables, compare. And then you get a qualitative sense of what works and what doesn't, but they're not just tunable parameter fitting tools. The second thing is, this is what, for example, with star-star binaries, Mo Di Stefano, you just have a, however simple or baroque model parameterized of what the mass ratio distribution, the eccentricity, etc. would be. Then you have an analytic model, you propagate it through, and you could imagine doing fitting. But you're left with the task of inventing functional forms for what's likely. Or I guess that is my version of hierarchical Bayesian modeling. Let's see what you can do to let the data speak to you. So to be serious, I actually don't know what will be the right thing to do if one had 30 or so good black hole candidates in Gaia DR4. All right, so let me now basically come to the point where I'd like to actually hear from you how you see this situation. I promised some of my own personal predictions, and I'll do those in a second. So I think it's, making sure you understand the objects that look really cool will be step one. And I think Gaia data itself has tremendous amount of information to double check yourself. I think external follow-up will still be a big deal, high resolution spectroscopy, etc. I think then there should be a phase of, let's hope that nature is kind, and half the papers will say those objects can't possibly happen, and the other half of the papers will say, that's exactly what I said in my 2022 paper. And so that'll be a fun, no, it's actually a productive phase of the game. I think here my conjecture is spectroscopic systems, I think, that look promising, where you look at the spectra, where you figure out it can't be a binary, a luminous binary, etc. There, I think that's a very promising avenue of finding new things that might not be totally obvious in the initial catalog. And then the other things, I think, there, it may be somewhat premature. I think then we should just wait, actually, what Gaia DR4 offers us. So here are my two statements before I want to hear from you. What do you think about this whole issue? I think it's a fairly safe bet we'll do an order of magnitude better on astrometry. We have two systems, and nature would be too cruel if Gaia BH3 was the only blast from the future. So I think that's a fairly safe bet that something's happening here. I believe that the fact that both spectra of massive stars have been censored so far severely, that we now get them with the single epochs, I think that may be, when it comes to actually linking also to the massive and short period thing, I think that'll be the biggest open new parameter space. Surprises, if I knew them, they wouldn't be. And I think the other message is, it's easily said, you can take all these individual data and double check or dig deeper, etc. I think all of us, for the things we most care about, should spend some time actually preparing some software tools. I mean, in some sense, this guy Mark has made a giant leap for the astrometry part. I think between spectral disentangling, right, there are codes around, but I think that's what will actually be important. So I think that's all I want to say, and so I'd like to hear from you, but I think my option is, I'm pretty sure it'll be pretty awesome.
Hi, thanks for the excellent talk. Lots of stuff to think about. This is Reed Essick from CETA. I wanted to go back to the trichotomy that you drew, if that's the word, between a different model, way you could model it.
Yeah.
I want to make the argument that all of those are the same thing.
Conceptually, yes. I mean, you envision something projected into the space of observables and see what fits and what doesn't, right? I think in the end, all of them have likelihoods. My sense is that the parameterized models, you need to enumerate all plausible models and go through them, right? And my impression is, but we'd be happy to be corrected. That is hard. I remember I think Casey showed, right, the little spikes in the mass distribution of black holes, right? Those you can't just shift around, etc. So conceptually, yes, I think in practical terms, it'll still make a difference what to best do.
I agree with that. I just wanted a small addendum to Reed's point that I think they could all be a they could all be implemented in a hierarchical Bayesian inference, if that's what you were getting to. That you could do a very strong population model in a hierarchical Bayesian inference. You could also do a parameterized model, and you could,
Thank you for saying that, because my response is there is so much gravitational wave brain power in this room. Consider putting one little leg over the fence, you know. That's.
That's amazing. You mentioned for the massive stars, you need to be careful about contamination. Can you explain what you're thinking about there?
So I guess an O star with a clear indication of a 6 solar mass companion, and I don't quite know whether I should have seen that 6 solar mass companion if I desperately try to disentangle, and then you tell me it's a triple, and you have a, you know, so that's what I mean. I think proving darkness is just, as you know better than anybody else here, is just hard.
Yeah, but the astrometry will help tremendously.
So I think for the astrometry is somewhat immune to that. That's correct. The question, I've been thinking more about the short period ones.
Agreed. And if you're considering only doing spectroscopic analysis based on the Gaia spectra without too much interferometric information, yes, you need to be careful.
Yeah.
Can you, Shai and Sharia, you showed some preliminary information from the future. Can you just quickly go over the key catalogs that Deepak will themselves publish with DR4?
I believe you're asking about the value-added catalogs. So technically speaking, the ESA website, and there are various ways to track down, tells you essentially what it is, but perhaps let me go back to here and say it in words, and if I'm actually imprecise, where was it? Yeah. So what's behind this shorthand? So it is my impression that all single epoch, let me talk about spectra first. All single epoch RVS spectra taken down to close to 16th magnitude will be published, even if the individual signal to noise is crap. Then all individual epoch XP spectra will be published. And then I believe basically all the individual epoch astrometry will be published. On top of it, there will be what's called the NSS, the non-single star structure, that will be slightly expanded, for example, the triple solutions, in a way that I actually don't know. I'm a fringe member of Deepak, so I don't know. And the other thing to say, as in all previous releases, it's likely that there will be a set of science verification papers whose purpose is to show what can be done without stealing the scientific thunder.
I want to go back to the thing you and Uk were discussing. What do you mean by short period when you say short period plus massive star?
How
short?
How short? 50 days or less.
15 days or
less.
Okay.
50. That's
50.
So,
okay.
Right. Basically, I would agree with Hug that if I can have astrometry, it feels better. But I believe there will be an important regime where you have plenty good enough spectra, and you see something going crazy, but the periods are short enough that you can't expect astrometry, right? And you can leave them, put them in the fridge, and first deal with the actual GUIs before you take the probable GUIs. Yeah.
Okay, yeah. So at the bottom end of that range, you should expect accretion maybe below the level of what's in X-ray binary catalogs, but yeah, in the middle of that range.
In a sense, I believe, obviously, looking at flux points at all wavelengths, if an object looks cool to you, is an obvious thing of asserting the nature and vetting, right?
Yeah.
So I think all of this.
Yeah.
And
What's it going to take to believe astrometric binaries without spectroscopic follow-up, without multi-epoch spectroscopic follow-up?
Faith. No, sorry. To be more, I do believe that indeed there will be astrometric binaries that look very good, are too faint to have RVS spectra, and may have one Lamoste, one SDSS5, etc. So I think there will be need for verifying this, and I think if I can go back to, right, so I think vetting would be another word there. I think that one should do diligence, yeah. And I should also say one of the things that concerns me is, and perhaps this is something you guys could do next week, there isn't really a particularly collaborative, concerted effort how to go about this.
Thanks, Maya Fishbach. Thanks for the great talk. I guess I'm wondering about this question of like the systems where you won't confidently be able to identify that it's a black hole. And do you understand the population of imposters or contaminants well enough to be able to like assign some probabilistic estimate of like what basically what we call P-astro and gravitational waves, and still use those systems for a population inference, even though you don't know they're real or not?
So I think that's an important point. I've grappled with this, and also I guess Johanna is grappling with this too, because she actually has said all the real things are in there, but the contaminants dominate. Now, can you deal with dominant contamination? The answer is yes, but you have to have a very good model for the contamination, right? So my feeling is that sociologically, we'll start out in the low contamination regime, which I believe there is, and then gradually push our way in there. But I think there are many things where the Gaia community should learn from the trials and tribulations of the gravitational wave community. So I think that will be very important.
Yeah, and I think the exoplanet community as well.
Yeah. So I should say, there's so much cool stuff on I mean, this is actually, at some level, a minute thing, fraction of what you can do with the Gaia data, right? You want to know how many Jupiters there are in the world? Okay, sorry. Okay, wrong crowd, I retract my comment.
Yeah, I have a question about the data products. When you look at the catalogs, there's a G magnitude, a BP, and an RP. Are we going to get separate astrometry in 3 different colors? Or is that eventually going to come, or is that
No, I did not
impossible?
go into how Gaia actually works. But astrometry fundamentally is actually only happening in the G band.
Okay.
What people call a BP color is the little BP spectrum integrated up.
Okay.
The RP, etc.
Okay.
Yeah, there's no, but I think, I haven't thought it through, but in thinking through what to believe or not about past microlensing events, I think actually, having this multi-epoch resolution 100 spectra or 50 spectra can actually be very precious.
Okay.
Okay, Selma?
Maybe slightly random thoughts. Maybe the first is not very serious, but for Dutch people, your acronym is something you might say while throwing dice. Gooi is to throw something.
Okay,
so I don't know what
so
that means, but that was not my comment. So one thing that strikes me is this is very object-oriented, as in identify your object of interest.
Yeah.
I guess my questions are more process or physics. What do we not understand about stars?
Yep.
And maybe this is the step to get there. There's one aspect, I think this comes from your talk, Karim, that I saw over the summer when you showed us the completeness. And so there's this weird thing that, please correct me if I am saying something wrong now, that Gaia has been sensitive to binaries with orbits that models don't predict. I don't think I don't know if I haven't been at every talk here, so I don't know how clear that came across in this conference, but it's predicting all these systems where binary interaction has happened, should have happened, and these distances should shrink or widen, or they should not be there. And so one challenge is that if you want to understand the completeness, but your physical model that you're using behind it is not reproducing this at all.
Yeah.
If you, so Compass or any other binary code, you can of course be more open-minded and think it's something else. But it's really weird. It's probing this area of binaries that should not be existing, and there's many there. And so I don't know at all what will happen if we go to other periods. This is not really a question or a comment.
Yeah, so
a random concern.
Actually, let me pick up on both points of view. So it is true that I have our focus on this. Can we just paint the empirical picture? Just because I think that is an indispensable step. I mean, your second point will also be that it may, if Gaia data populate part of that space that you think shouldn't exist, I'm delighted, it's your problem. I mean, that's, but I mean, I think GUI should be flushed soon, but I think it is worth thinking about the terminology, because I think we don't want to have, it's good. I mean, Kareem, did you copyright the BH? No, you didn't.
You have to apply for a number when you have a GUI.
Oh. Can I pre-purchase 11? No, so I think it's an interesting question on how to do this, because in some sense, right, Gaia is much less, the gravitational wave experiments are in some sense much more centralistic, right? Here, stuff is put out, and anybody can do whatever they want, right? From the get-go. So I don't know. I don't have a good answer. I put this out at some level as a provocation that we need to think about this.
So maybe for the modelers, although this is obvious to the people doing this already, so we're trying to come up how to make this Gaia black holes in all kind of ways, but as soon as we extend the parameter space, I think that's where the tests come between the different solutions, right? Because we have different distributions there.
Okay, one last thing and then I'll shut up. I mean,
I'll give this away.
2 days ago, at dinner, I think it was Korea said, okay, it's remarkable how many explanations have come up for 3 Gaia black holes. We'll see what happens if there are 30. And Karim said, there will be fewer explanations because many are ruled out. So I think that's a good thing to actually ask whether the more observational constraints will actually.
Okay, there are like so many hands up, but I'll try to get to you, but maybe Vicky, you can start setting your thing up. I first saw Reed, but you already asked a question.
Hi, Carl Rodriguez, UNC. I actually wanted to follow up on that, which is, I think we're in a slightly different regime than the gravitational waves for 2 reasons. One, we're going to get slightly fewer events, but 2, we're going to have more information that is useful to us modeling individual events than we do in gravitational waves, right? We'll have metallicity, period, eccentricity. And so I think we actually will gain a lot more information faster on a per event basis than we do in gravitational waves. Part of the reason we've all been able to hide our models in gravitational waves is because you can tune things on a population level much more easily than you can in an individual system. And so I actually think I wouldn't do forward model populations. I mean, I've done those for Gaia before, but that just gives you good forward predictions. I think what we should actually start doing is take individual systems, model them forward using our various formation scenarios, and then start to rule out how the parameters that control the overall evolution, like, determine individual systems. And I think that's going to help us make progress a lot faster than the gravitational wave side.
Yeah. So wisely spoken, I agree that one of the beauties of this is you can always gather more information, you can follow up, you can think of new tests and actually execute them on the same system at hand. That's right.
So I know this conference is on black holes, but like, what are the prospects for neutron stars and DR4, especially around massive stars?
I believe the prospects are excellent, and I think neutron stars should get more attention.
But let's thank Hans Walter again.